Hi everyone, welcome back to session 4 of the Worldcoin Educate Series. We're nearly halfway there now. Today we've got a talk on biometrics, and I know you guys had a lot of questions on Monday about this topic, so do make sure that you put them in the questions tab because our speaker today is the one to ask about these topics. Hello, thank you for joining us.
Hello, Rebecca. Thanks for having me.
I will lead the stage and you can begin your presentation. I will be backstage if you need any support.
Awesome. Cool. By the way, Rebecca, should we wait a few minutes for people to join, or is everyone going to be assumed to be here?
I think we've got a pretty full room already. There's quite a few names in this list, but you're welcome to wait a minute or two, introduce yourself, have some small talk until the room is even fuller.
That's perfect. Sounds good. Thanks. All right. So my name is Tanguy. I'm engineering manager in the AI and Biometrics team at TFH. So basically, I'm contributing to the team and I'm managing the team that do anything iris recognition related and other biometric data processing related on the orb. Put it here behind me. You might see me moving around a little bit. I just broke my feet a few days ago, so I'm still trying to get used to that new setup. That's also why I'm at home and not in the office. But yeah, I think I can actually get started. So let me share my screen. Cool. I'm going to assume that everybody see my screen. Rebecca, just interrupt me if there is anything going wrong.
We can see your screen.
First of all, thanks for joining me on that little talk. My goal here is to unveil the mask on what's happening on the orb. What are biometrics in general? Why are we using biometrics in the first place, actually? Because honestly, our life would be so much easier if we wouldn't deal with biometric data. So why have we put ourselves through that path? What is important to know around biometrics? Some design decisions. Why have we chosen iris and not fingerprints, for instance? And also, talking about iris, given that it's one of the core components of the project, I'll tell you a bit more about how iris recognition work as well. I'll try to start as high level as possible so that people won't need to have a mathematical background to understand what's going on in general. But I'll still try to drop some nuggets here and there so that those of you that do have the background could maybe connect some dots around what's happening, what are we doing with biometrics. And if we have some time in the end, I'll show you also what we've open sourced, because we're actually proud of it, but my team and I, we've open sourced the whole iris recognition engine that lives on the orb. Given that our whole ethos, our whole mission is to have everything as open source, permissionless, and decentralized as possible. Even that usually companies keep very private and secret, we've decided to open source it. So if you have some time, we'll go through that as well. And of course, I'll take questions, probably something like halfway and then in the end. So do drop all of your questions in the questions section, and anything that I'll try to answer to everything that's like biometrics related and iris related. So first thing is, I know we've had like an entire session, I think, on introduction to Worldcoin. For those of you that might have missed it, I'll go through it quickly, my own spin of it. Why we're doing all that, what's the core added value of the project, in my opinion, is that we're creating a system that allow to verify and characterize humanness in the age of AI. Why in the age of AI? Because with all of the models that are out there, open source or private source, to generate data at large scale, how do we know who's a real human and who's just a bot? When every signal can be falsified, how to know which signal actually comes from a real person? And I think that's a huge primitive that we're completely missing today. And that's why we're having social medias, for instance, that can be so overcrowded with bots, fake opinions. Basically, we need to reintroduce a bigger notion of truth and humanness online without compromising on anything privacy related. And that's, I think, why the project is so cool, because it sounds super counterintuitive to have at the same time strong authenticity, strong authentication, and strong privacy at the same time. So basically, I'm not going to teach you anything when I tell you that any data can be generated by AI models. Text, for instance, now it's virtually impossible to differentiate between AI-generated, LLM-generated text and human-generated text, which is a huge source of potential fake news and a bunch of, let's say, societal issues linked to that. But text is not the only modality that can be generated. Images as well. This one is one of my favorites. I used to use this exact same slide, exact same example already 5 years back. For those who don't know, this is a website called thispersondoesnotexist.com, which relies on StyleGAN, which is a GAN, so generative adversarial network, an AI model that can generate data that resemble distribution that has been shown. And so typically these three pictures are completely AI generated. And five years ago, as the same as today, I still can't believe that we have models that are like that good. And plus, we also have tools to make sure that these models don't just copy paste the same images or mash up together parts of different images into a new one, but those are purely created out of the blue. So text can be generated, images can be generated, video can be generated. I'll go through this one real quick, but you've probably seen this video also from OpenAI. This is entirely AI generated. For those who don't know, this is the Sora model who's been showcased in February. To be fair, we're still waiting for having the model being available for everyone to use. But when the model works like that good, I understand that open sourcing such model should be done very cautiously, because this could be used to completely manipulate what is true, what is real online. Yeah, all of that is pretty AI generated. So given that we're in such a situation, how can we make sure that we interact with a real person online? How can we verify that our interlocutors are not a bot, but a real person? This is what proof of personhood is about. Again, I'll scroll through that real quick, but proof of personhood is this notion of verifying, are you an authentic and unique person? We don't want to know who you are. We just want to have some verification, some certainty that the user we're talking to is a real person. The rest, I'll scroll through that because you already had the presentation of what is Worldcoin, number of users, blah, blah, blah. Part of our infrastructure. I think you had a nice talk from Dan on anything org related. And so I'll be here to cover the part on biometrics. So first of all, why biometrics? What we're trying to do is proof of personhood. So proving that you are an authentic person at scale. Authentic here should be understood as both human, like a real 3D person that exists in the real life, and unique. We need the uniqueness because otherwise it's just so easy. If you don't have a notion of uniqueness, you can just generate 100,000 millions of such key and flood the market with those, flood internet with those in such a way that it would only take one person that would distribute these keys at high scale for the whole system to stop working. So we really need both the humanity and the unicity part. And the at scale is what makes the whole project super interesting, because we decided that we won't just do that in one country, in one continent, but at the scale of the world, because we're, again, directed towards fairness, absurdly extreme inclusivity. So we need to have, we said up to 1 billion users. So that was the very early day target number. Our system is already wired for orders of magnitude above that. But let's say that saying 10 billion users while you don't have 10 billion humans, and we barely have, I think, 3 or 4 or 5 million, a billion humans that have access to internet. Also, let's not get ahead of ourselves. So that's why 1 billion is here. Borderless, we shouldn't rely on one country's identity system. we could integrate it, but that shouldn't be the basis of it. And unforgeable, so we shouldn't be able to create fake statement that I am a real person. So now, if you have to prove that you're human and unique, how do you do that? The underlying question is, what makes us human? So you could have some theoretical answer based on what humanity means at the core. Compassion, empathy, helping each other, all these kind of values that are, I think, great and subjective. But beyond that, we're not trying to say what makes us human, as in what is the ethos of human, but what proves that we are human. How to prove we are a human? What characterizes us as a human? There's not many things. There is actions we could do. There is things we could type, pictures we could say, but all of that, as we said before, it can be falsified, generated at scale. So it's paradoxical because we're in a situation where we want to protect ourselves against a flood of data, of generated data. But how do you verify you're a real person? What data do you base yourself on? Because all the data that you could use for authentication, like a picture of your ID or a selfie where you say yes or no, these kind of things, they're good, but they can be faked at scale. So given that this kind of like a chicken and egg problem, we had to cut the middleman, basically, and say, we have to measure ourselves that there is a real 3D person that we've never seen before in front of a hardware that we can control. And that's the key, controlling the hardware. That's why we've been building the world. So now that we have this idea of we need to have the owned secure hardware in front of which we're gonna, in the real world, measure is there a real person, measuring humanness, measuring thing on a human being, it's biometrics. All that to say, we're doing biometrics because we need to measure in person that there is a real person in front of a control device. But now, given that this is the idea, the statement of the project, what do we do? What kind of biometric modality can we use? The first thing is, getting into biometrics, there's 3 ways to use biometrics identity system. The first one is verification. I'm Tanguy, I'm a person, and I want to prove to a system that I'm really me. Let's say I want to prove a database that I am Tanguy because of my passport, in which I have my biometric picture. What I'm going to do is give to the system a new sample of my biometric data. Let's say I'm in front of the airport. The scan knows in the biometric database that this face equal Tanguy, and so I'm presenting my biometrics in front of the camera so that they can sample the new picture and then match the 2 pictures. So verification is how the vast majority of biometric systems are used, because it's one-to-one. I say, hey, I'm Tanguy, here's my biometric to prove that I'm really who I claim to be. Then you have identification, which is 1-to-N. This one is a bit trickier. The idea is you have a database of N persons, and you want to know if anyone, are you in the database, and who are you? This is more often used in use cases, typically in forensics. You find fingerprints on a crime scene. So you sample these fingerprints biometric data, and you match them against an entire database. So 1-to-N because you have N already registered offenders database or something. What we're doing is a bit different. It's identity deduplication. The idea is, hey, I'm here, I'm Tanguy. First time that I'm coming to sign up to Worldcoin, I want you to be able to verify that you've never seen me before. So given a database with N identities, I want to make sure that I'm not yet in the biometric database. That's identity deduplication. And the good thing is that it allows us to kill all the nefarious use cases that's often associated with biometrics in the egg. Typical negative use cases could be things like mass surveillance or whatever. We don't want to know who you are. We just want to make sure you're not yet in the database. So then we can use some cryptography techniques like zero knowledge proofs that you might hear about in the next session, I think, or in previous one, where basically you can prove, hey, my identity belong or do not belong in the set of known identities without knowing to whom it matches. So by these fancy cryptographic tricks that you'll see in a moment, like in a few days, we are able to kill all these negative use cases. Plus, with things like secret multi-party computation, we can make sure that we don't store the biometric themselves, but mathematical artifacts of it. Anyway, so identity. We have to do 1 to n identity deduplication. And that's where things get actually interesting, because let's say that if I have 1 million users already registered, and a new one wants to arrive, I have to check that the new one is not user 1, not user 2, not user 3, not user 4, up to user million. So basically, I'm going to roll the dice 1 million times on knowing whether I could get a wrong answer from the system, because systems inherently can never be perfect. So given that we have systems that could never be perfect, and that we have up to 1 billion users that are necessary, if a new user comes in with 1 billion user in the database, but nobody gives a false match, it means that all the billion users have to not match. So basically, you have to multiply your false match rate by 1 billion. I'll come to that in a second. So these are the 3 metrics we're interested in. 3 metrics that allow us to characterize the biometric system: false match rate and false rejection rate. I'll start with the second one. The false match rate basically is what I was explaining. What is the probability that a user will be falsely matched with someone else? We want up to, let's say, 1 billion users in the database. So if we have a once in a million probability to be false match, then we can't reach that database size, because at 1 billion user, if 1 in a million gives a false match, we'll have thousands of false match. This is not acceptable. So what do we need our false match rate to be? Extremely low. The false non-match rate is the probability that you're already in the database, but we can't match you back with yourself. In that case, you're able to get a second world ID. This one also we want it to be as low as possible. And the false rejection rate is, what is the probability that the user will be falsely rejected by the security in the spoof model? Those that make sure that you're a real 3D breathing person. All right. I just noticed that I've swapped these two in the slides, but basically, the false match rate, we need it to be at 10 to the minus 12. 0.1%, because if we want 10 to the 9 user, 1 billion user, and we want that this billionth user get rejected rarely, like once in 1,000, we need this to be 9 plus 3, 10 to the minus 12, so 1 in a trillion. False non-match rate, so this one we're swapped. We want that it should take 100 times trying to send up at the orb for generating another false world ID. In practice, this one is much lower, but this is the bare minimum requirement. And the false rejection rate, more or less, we want that rarely, like 5 or something % of the user will have to try a second time. So that's our requirements for the biometric system. False match rate of 10 to the minus 12, false non-match rate of 10 to the minus 2, and false rejection rate of 5, 10 to the minus 2. So given that, we can have a look at the different modalities. Modalities are things like fingerprints or face recognition, DNA, iris, palm print, whatever. Basically, we found that iris was by far the best choice for our project for a bunch of reasons, all but here. Basically, it's hard to forge an iris. There are some very painful surgeries to change the color of the iris, but this is so expensive and so painful that it does not make any economical sense for a user to do something like that. Not so very hard to modify it. It's easy to see if it's a real iris or not. Computer vision models can detect that very easily. The scalability is the most important thing, because iris has such a huge amount of entropy, such a huge amount of randomness in it, that it contains so much information. It's not very, but it's easy to distinguish two different persons at 10 to the minus 12 target false match rate. Recently, palm print also became a modality that started to be used, like by Amazon One, for instance. we still are to be seen a use case where such database can scale to billions of users. I think it philosophically should be possible, but Iris has been proven. We have some databases that are in Aadhaar, for instance, the Indian social security system, which is iris recognition based, for instance. So Iris, we know it can scale. And so last thing around iris recognition, and then I'll answer some question very quick, is we have two eyes. So how does that compare? Are the two eyes completely independent? How do we ensemble that information? The first thing is, one reason why we're not using face recognition to create World ID is that face recognition has false match rate in the order of anything between 10 to the minus 4 to 10 to the minus 8, depending on the data quality. Iris can easily get to 10 to the minus 6 per eye. In practice, we are 1 to 2 orders of magnitude below that on our prediction system. And so when you ensemble these two information, when you want one eye to match and the other eye to match, basically you are multiplying the false match rates. And because the two eyes are completely independent one from each other, it means you can properly, by the intersection of the two is the multiplication of the two. So in a nutshell, how do we ensemble those two? Both need to match for it to be considered a match. The effect is that it doubles the false non-match rate, but it squares the false match rate. So 10 to the minus 6 squared 10 to the minus 12, we can reach our target pretty easily. And so compared to face, Iris is much better because your left eye, your right eye are completely decorrelated. Your right eye and your father, your daughter, your brother's eye, iris information is completely different. While for face, you have some similarity. Twins have radically different irises as well. There's been some research quite in depth to prove that. Basically, as weird as it can seem, the information on your two irises is completely decorrelated apart from one very high level factor that's minuscule compared to the quantity of information, which is the color of the eye and the type of pattern that you can encounter. Unless you have dichromia, which is two eyes in different colors. The other way to ensemble those would be, I need either of the eyes to match, but as the graph on the left shows, that just cannot scale to the number of users that we are targeting. So that was for the identity part. And then on the orb, we've added a bunch of additional sensors for authenticity. So verifying, is there a real 3D breathing, living human being in front of the orb or not? So we have these sensors here plus a few on the orb, but basically RGB camera for seeing, well, is there a human face or is it like a dog or is it feet or something? Thermal camera for making sure that we have the heat signature of a real person. 3D sensor to make sure that it's not like a sheet of paper with the photo of someone, but it's actually a 3D person, all these kind of things. And so for all of those, we have dedicated AI models. I won't get too much in details right now, but if you have questions on those, I'm happy to take them. All right. So before getting on how does iris recognition work, I'll take a few questions. So what do we have here? Why do we need to identify human or not? Isn't the whole point of cryptography to stay anonymous so no one knows who you are and what you do? Thanks, Mike, for the question. The whole point of what we are doing is to stay absolutely radically anonymous. So using a world ID does not reveal anything about who you are, who you know, what you're doing. But the creation of a world ID is linked to this being in front of the orb, which shows that you're a real person and a unique person. Why do we need to identify human or not? Because otherwise you could maybe generate a world ID for a sheet of paper, inanimate object, for a pet. The pet use case, I could see something going in that direction, like veterinary identification or like live blog, like live journal of health of a pet, for instance. But that's another use case. That's not what we're trying to solve. We're trying to solve Sybil resistance. So we're trying to solve cases where I want to make sure that I'm only having authentic, real users. If we would accept world IDs for inanimate object, for instance, that would negate the added value, which is making sure that you're talking to a real person, not talking to a bot that is trying to sell you salt, bath water, or something like that. And then we have another question here. Is iris code or mathematical representation essentially a biometric template? Yes, absolutely. I'll come to that in a moment. But a little spoiler, an iris code is the mathematical object we're using to identify who is who below the SMP cryptography layer. And so heterochromia, which is different eye color, it's not a problem at all. It just makes that the two eyes will have even more difference between themselves. But you can have the eyes of a different color, and that's absolutely fine. And for blind people, that's a good question. So there is some people that are blind and still have irises. There are some people that, due to some disease, cannot have two irises. And we can't expect every single human on Earth to have two valid functioning eyes. The whole point of the project is to be as inclusive as possible. And there is no biometric modality that can be guaranteed to be 100% possessed by everybody. So we're currently working on a side enrollment stream to make sure that we can use other biometric modalities to enroll people that do not have two valid functioning eyes. All right, I'll get back to the presentation and I'll take the other questions later on. So, how does iris recognition work? Beyond just the title of this section, it's also the title of one of the original papers that created iris recognition. And the history of iris recognition is actually pretty interesting. It was pioneered in 1993 by John Dogman. And for anything biometrics related, for anything recognition related, like face recognition, for instance, 93 is actually super early. And in 93, we already had amazing results. The reason for that is that inherently, pupils and irises are just round. So you can have some very computationally light method that are not the most reliable, but that were good enough to identify where in an image is the iris and the pupil. And from there on, use classical computer vision method to extract the information of the texture. That's actually what John Dogman did in 93. Since then, the field evolved a bit, and I'll tell you a bit about that in detail. What I'm going to present to you is the current, more modern approach that we are using, including some innovations that we've built here at Worldcoin. The pipeline is the following. The first is there is a few images that arrive that are taken on the orb. By the way, all the images that you're going to see here, all the biometric data, of course, come from either employees or have been taken in the laboratory. So none of that is user data. That goes without saying. So given iris images, we first evaluate the quality of the image. So we have a few neural networks that deal with the autofocus, with the tracking system of the iris, to make sure that we have consistently like a frame where the iris is super sharp and in focus. When we have images that are in good enough quality, so not blurry, the eye is open, etc., we pass that into the segmentation model. It's basically the model that's going to say, hey, here is the iris boundary, here is the pupil boundary, and we're going to use that information to unwrap the iris and turn that into an iris code. So starting at the segmentation part, because this one is just an AI model that gives you a quality ranking. We start with an image. This one actually is a photo of my right eye. The orb takes images in the near infrared spectrum. Near infrared is roughly 850 nanometers. Why infrared? Because if the majority of the human on Earth, you have brown or dark eyes, that information is very hard to see in the visible spectrum. If that's the case, you can look at your eye in the mirror or ask your friend, okay, can I look at your eye for a second? Promise, it's not going to look weird. And so you just see brown. You just see brown or black. And on the visible spectrum, it's very hard to see the details. while in the near infrared spectrum, this is where all of the texture richness come to life. So for some reason, the iris texture is much more clearly visible outside of the visible spectrum. So we take that image of my right eye. How can we turn that into the iris code that you were talking about, which is the zeros and ones that mathematically synthesize the iris texture of the person? The first step is you're gonna know where is the iris. So given the iris image, we have a first deep learning model that's gonna say for every pixel of the image, what's the content of that pixel? Is it green? So is it an iris? Like here, is it pupil? Is it just the skin? So gray, nothing in particular. Or is it eyelashes? Or is it the sclera, the white of the eye? The eyelashes is actually necessary because some people can have the eyelashes that point not upwards, but more downwards. And these eyelashes can hide the iris texture. We don't want to extract that information because it's not biometric information that's constant. Because you can close, open your eyes. When it's closed, when it's blocked, when there's something occluding it, we don't want to deal with that information. I don't know if you can see it here, but the green part this is purely model generated. So pixel per pixel precision of saying where does the iris texture start and where does it stop. Once we have that information, we can go to the normalization step. Oh, and by the way, I have much more information on the segmentation model if you're curious in the annex after that on the question section. Then we normalize the image. The thing is, the iris looks like a donut and it's not the most easy to process because the iris could be on the top, on the bottom, left, right of the image. It can be bigger if I'm closer, smaller if I'm further away. It can be tilted on the side if I'm tilting my head. So there is a bunch of things that varies. The pupil also can constrict more when there's a lot of light or dilate more when it's dark. So the normalization step basically erase a good chunk of this variation. What you do is that you're gonna artificially cut the iris texture at some point and unwrap it. So what you can see here, that's the lower eyelid in the schema that you could see here. That's the upper eyelid in the schema that you can see here. This information here, like all that which is straight in the Cartesian plane, when you put it in the polar plane, it's gonna look warped. So these bumps you can see here are actually my lower and my upper eyelid. The little black thingy you see here is the eyelashes, for instance. And I don't know if you can see it, but here I had a bit of eyelash that was going over the iris texture. This is garbage information, so this is also blacked out by the model. But this image is mostly clean. And once we have it, once we have this stable piece of biometric data, how do we process it? We have what we call Gabor filters. Gabor filters, if you're also familiar with quantum, you might have seen them around because the probability distribution function of a particle also follows that. A little bit of trivia, unrelated. Actually, I'm gonna go over to one of our web papers that explain that better. You can find all this material open, by the way, all more detail with more talks or more thoroughly explained. All of that is available online. I wanted to also show this one in particular because to show you what a Gabor wavelet looks like a bit better. That is a Gabor wavelet or a Gabor filter. Basically, it's the mix of a Gaussian filter, which is going to encode some form of locality, and a sign filter that's going to encode some form of periodicity. This is what a Gabor filter looks like. You can have a bunch of them. They can be tilted on the side if you want to have some information at an angle. There is basically a whole family of them. This is the Gabor filter family. And how are those any useful? Well, those are complex valued. So they have a real and an imaginary part. The real part is symmetrical. So it's symmetrical between that part and that part here. These basically can be used as a form of line detector. The imaginary part is anti-symmetrical. So negative on one side, positive on the other side. And this can act as a form of edge detector. So when you apply a Gabor filter at one point of the iris texture, you're going to receive a complex value. you can lose the majority of the information. Actually, we drop the majority of the information. We only keep the phase, which is like what is the angle of that complex vector. And then we threshold it, we quantize it. Basically, it's going to look at, is the imaginary part positive, negative, and the real part positive, negative. So how to interpret that? How to interpret that is basically the real part is going to say, assuming there is a line here, is it more to the left or to the right of the filter? And the imaginary part, assuming there is an edge here, is it more to the left or to the right of the filter? That's in a nutshell the information here. So it loses the majority of the information. From the iris code, you cannot reconstruct the original iris image, if that wants to load. You cannot reconstruct the original iris image from the iris code. But the iris code basically contains enough information on the iris texture so that when you take another picture of the same person another day with much more light, with some fog, the person is crying or smiling or they're wearing a cap or whatever, all these modifications make that the new iris code generated will be mostly similar. So going back to the presentation here. Another question is, what does it mean, mostly similar? We need a way to identify whether two iris codes are the same or not. We can't just hash it because there is always going to be some differences. A bit can be a 0 here, but a 1 next time, because inherently you're having like a real life process. So you're gonna use a sensor, so the iris texture can be different. You can have sensor noise that's different. So for a bunch of reasons, at minimum, 10% of the bits are going to flip from one time to another. Actually, it's not that much, it's not a lot, but we can't just hash the information, we have to compute a distance. Bunch of different ways we can do that, but we're really using Hamming distance or fractional Hamming distance. It's basically the proportion of visible bits that are the same. It's just that you count the times where the two iris code agree and the times where they don't disagree. And you divide that by all the relevant iris texture area, because you're not going to take that information because the idea is just covering the iris texture here. So we look at the Hamming distance. That's what I was explaining here. So if the two are completely the same, the distance is 0 because there is no distance between them. If they're all different, the distance is 1. And in practice, it's always going to be something. It's never going to be 0, never going to be 1. The interesting thing is the following. The statistical properties of the Gabor wavelet make it that it's a toss of a coin between a bit being a 0 or a 1. So if you take two iris codes that are completely different, basically every time you're going to compare the two bits, it's a toss of a coin. So 50% of the time, because it's 0, 1, 1, 0, 50% of the time one's going to say 0 and the other also going to say 0. 50% of the time, the 0 is going to be a 1. So if you have a Hamming distance between two iris code of 0.5, that's actually in average. It means that those are super different. They're completely random, one for another. So how do we measure our biometric system performance? I'm going to skip that slide for now. How do we measure the performance? Basically, we have a graph that goes from 0 to a little bit above 0.5. And we're going to take a bunch of iris images where we know who is who. And then we're going to compare the information of what we know who is who and what the model is telling us. And we are always expecting some errors. It's never going to be perfect. So there's some times where two different irises are going to, just because of luck, have an iris code distance, Hamming distance, below the threshold we decided. That's the false matches. And the false non-matches is when we have twice the same person, but it's above threshold. And so how does this distribution look like in practice? So we basically gather some data in our lab, and we gather, I think it was like 1.5 million pairs of iris images. Again, no user data, only test data. And this is what the distribution looks like. Basically, what are we seeing here? We colored by what are the real non-matches and what are real matches. And in the laboratory, setup where the conditions are good, everyone is friendly and cooperative, there is a wide gap between the matches and the non-matches, which means that in the cooperative, a nice, friendly, well catered for, good everything case scenario, we have an absolute perfect system. And that was like with more than 1 million pairs of iris images, so quite some data to back up that claim. And in fact, we see 2 bumps here. That's actually fun. This bump here is 2 images, 2 iris images from the same eye, from the same person, but taken a different day. And these are images taken from the same sign-up. So the conditions are very similar. It's just mostly sensor noise. And this, like, the peak is at like around 0.08. So in the everything looks good case, we have a system that is ungodly performant because that's logarithmic scale. So that is like 10%, that's 100%, 1%, 0.1%, etc., etc. So the curve looked much more even skewed on the linear scale. And in the case that's in the field where things are more rough, even that the false match rate is at this. False match rate per eye 10 to the minus 8, and false non-match rate per pair of eye 10 to the minus 5. So our target is 10 to the minus 2 here, and here we want the square of it to be below 10 to the minus 12. 10 to the minus 8 square is 10 to the minus 16, so we're very good. All right, and then real quickly, and then I'll take some questions around open iris. So basically, everything that I've showed you is data either from my eye or from my team and the test data set. Basically, we don't want people just to trust that we're doing good work. We're open sourcing everything. This is already benefiting to the research community where people are reaching out to us on, they want to use that for eye disease research where they can identify easily, automatically parts of an iris, for instance. So we built everything open source, and well, here's all the great thing about it. Basically, the only other open source iris recognition framework that exist are usually not so well maintained. They're old school. They haven't been modified in 5 years or something. So what we're having is something that works out of the box because it's deploying in production on the orb. It's completely configurable. It runs on the orb, Linux, Mac OS, Windows. It's Python based, but there's a lot of Rust and Go. We can work on GPU, etc. So a lot of fancy stuff that you can do with it. That's an example. That's the right eye for one of my teammates. So the segmentation model is going to tell you where the white of the eye is, iris, pupil, eyelashes. Intermediary steps, segmenting out the noise, so like the eyelashes or the white reflections here. And that's how the normalized texture looks like. There is a lot of information you can get here. And this is basically what enabled us to create some iris code that represent the person's identity. And so when compared to literature, basically ours is above all the commercial iris scanner that existed some time ago. And I'm still computing the latest result, but it's still pretty much in the same area. Iris recognition have not evolved so much in the past 10 years. That's compared to other open source methods. So that's a big overlap. Ours, there's some overlap because the data is not perfect, but it's much less, etc., etc. That's some difference between traditional iris scanner data. That's an open source research data set. So you can see that the image is very grainy, very low quality, versus the same thing but on the orb, where this is the amount of detail that you have on the iris texture. And maybe I think I can show you and then take some questions how to use it yourself if you're interested. All right, so basically we, on top of open sourcing the framework itself, you can find it on GitHub, Worldcoin/OpenIris. We have a bunch of documentation and a bunch of tutorials also available there. So I can rerun all of that, but basically that's running everything from scratch. going to take a moment for running everything. All right. Let me scroll back to the top. So it's a Python package, so you can just install it with pip. You can see all the dependencies here is actually lightweight. Mostly we use the Hugging Face Hub because the segmentation model is open source, also available on Hugging Face Hub, Matplotlib, NumPy, typical Python dependencies, a bunch of others, so that's good. Latest Aries version is 1.1.1. Make sure you have this one. So same image, that still is the image from before, so my right eye. When we put it in the pipeline, this is the metadata that we get, so we can see how much am I looking straight to the camera or away from the camera, how open the eye is, where the bounding box of the eye is, etc., etc. And so how is it looking like? So that's my iris image. That's some iris code produced by it, parameterizable. And then the segmentation model that identify where the eyelashes are, where the pupil, iris, and the sclera is. And then put that in normalized image. You can't see it super well here, but I haven't adjusted the contrast of the image and the iris code. All right. I'll go to the questions now because there probably are more by now. So, why choose iris when thumbprint is also unique? That's a very good question. So you have the fingerprints, the thumbprint, the index print, all of that. Basically, even when you take all of your 10 fingers all together, the false match rates, the probability that you're gonna get matched against someone falsely, is 4 to 6 orders of magnitude higher, if I'm mistaken. That means that we basically can't have a billion users, but we can have at maximum, I think it's something like 10 million users, or 100. So basically we cannot scale to a project that is at the world scale with only these. And then we could have all the fingerprints, plus the iris, plus the face, plus everything. But the more you add biometric modalities together, the more you improve the false match rate, but the more you worsen the false non-match rate. So then we're going to have a system that is equivalent, but then it's going to be much easier to fake your way through and get several world IDs. All right. Are these radiations harm for the human eye? Radiations, I assume you mean the 850 nanometer near infrared wavelength. And of course, this is not a problem for the human eye. The sun has some infrared. When you go to this heated lamp, that's infrared. Infrared is convey a lot of energy. So we've of course made all the necessary to make sure that the orb is completely harmless to use. How does people with eye operation after cataract would be recognized, say, authenticate? So that's a very good question. So cataract in and out of itself, the cataract operation doesn't affect the iris texture too much. But there are some diseases or some operation that affect the iris texture a bit. We are currently cataloging all the possible eye diseases, all the corner cases, all the edge cases, and we know that it's like a very long process, so we're working with medical professionals for that. But at the moment, we've identified diseases that are either not interfering the iris texture or interfering a little bit, but that iris recognition still work on them. In some rare cases, I'm pretty sure that there should be some diseases that change the iris texture enough that we can not match the person back with themselves. So some of that must exist, but so far in all of our experiment, it's nothing that affects the viability of the product. What other organs or aspect of human can provide good enough entropy for biometrics? That's a very good question. I think the one that has the highest entropy is DNA, because there's so much bits of information in DNA. We've decided not to go in the route of DNA because it's not just like the way this part of your body looks like. It's not just like the iris texture, it's encoding everything about you. And so we've deemed that the risk of sequencing DNA on the entire human population was just way too high. Iris in and of itself is just like a centimeter squared, more or less, of texture, which is much more harmless. Fingerprints would not be good enough in and out of itself. Face is not not good enough in and out of itself. Palm print. So when we started the project, this was definitely not a research subject, or like very marginal. By now, I think palm print could work at scale, but we still have not enough research, not enough backlog to prove that. Amazon One, so it's a service of Amazon where you can replace your credit card by your palm print, is going in this direction. And so I think we have good hints to say that palm print could work theoretically. But again, we don't yet have the guarantee, not the research, not the papers that prove that at a high enough scale. And then you have, also to follow up on that question, you have a lot of biometric modalities that are called weak biometrics or soft biometrics, which are things that they really don't have enough entropy to identify you properly at scale, but they could bring some information. Typically, ear. The way your ear look is nothing remotely as good as fingerprints, which is nothing remotely as good as irises, but it still brings some information. There's been some forensic analysis that's been conducted on that, where somehow they could find like the ear shape of someone that committed a crime, and they could eliminate some potential candidates because the ear just looked too different. Gait is one, the way you walk. Right now, I don't walk, I limp. And so if you have a model that can identify that I'm walking that way, it can say that, oh, this person likely is having a cast on the feet, for instance. So not enough. Would a full body scan be a good example of providing entropy? So it depends what you mean by full body scan. So the first thing is your biometric modality must be stable enough through time. Irises is amazing for that because the iris of a baby up to when it becomes an elderly, the iris is not changing. There are minutiae that have been measured to change slightly, but nothing any relevant at the scale of iris recognition provides. So iris stays the same. Your palm line, when you're a teenager, change a lot. When you're an adult, are roughly stable. Full body scan depends exactly what you mean, but your posture can change a lot. You can get much more bent as an elderly, so the ratio of the length of your spine to the length of your arm, for instance, will change because the spine will dampen a bit, for instance. I'm not aware of research that's been done on full body scan, or like on this side of the entire body. I'm pretty sure there would be good enough elements to do some form of verification, maybe identification, but I don't think it would work at like the scale of mankind. All right, first question, why can't the orb verify only one eye and generate only one iris code? And is it possible to pass orb verification successful while wearing contact lenses? So those are two very relevant questions. Why can't the orb verify only one eye and generate only one iris code? Technically, it can. You can do an iris. You can generate an iris code for only one eye. But what happens then is that if you want to have a false match rate of 1 in a trillion, which is a necessary condition for having a working system at up to 1 billion users, so false match rate of 10 to the minus 12, 1 in a trillion. In order to have that, there is not enough entropy in one eye to do so. Or to be precise, there is enough entropy, but it's always a trade-off. You could get your false match rate down to 10 to the minus 12, but then your false non-match rate, so the probability that you won't be able to be matched back with yourself, will jump a lot. So you could have a system that have 10 to the minus 12 false match rate, but then with only one eye, it's gonna be so much easier for you to just spam the system and get multiple iris codes that it's not an option. So it's something that we physically can do, but we decided not to because it would threaten the viability of the project at scale. And then your second question, is it possible to pass orb verification successfully while wearing contact lenses? I was actually waiting for this one. Because if I go back here, right, let's take that iris image, for instance. Right now, it's visible. You can see the iris image pretty well, pretty clearly. But what happens if you wear contact lenses? All right. Trying to get back to that image. Okay, let's take this one. What happens when you wear contact lenses? So it depends which type of contact lenses. You have the daily contact lenses, the soft one. The soft contact lenses, they're barely visible. It just adds like a ring around the iris very slightly, but it doesn't jam with the iris texture. I don't have actually examples of that, but I could have thought of bringing some here. Then you have hard contact lenses, those that can be last up to a year. These ones are smaller, and those jam the iris texture a lot. So we have an AI model, another convolutional neural network that detects those and filter them out. So in that case, we're able to say to the user, hey, we can't enroll you, please remove the contact lenses. And then you have the cosmetic contact lenses. So I don't know, Naruto's Sharingan, or like an eye that's completely blue or black or white or red. Naturally, those will come on top of the iris texture. They're gonna hide the iris texture completely. And that is something that we cannot accept. Of course, you're free to wear contact lenses, you're free to use them to improve the way your eye look like. No problem with that. But you just need to remove them to pass the verification of the orb. Otherwise, that would just be rejected. All right. I think I answered to most of the questions in there, in the question part. I can have a little look at the chat, but I think we're arriving next to the time limit anyway. So Brian, you asked what are the privacy implications? I'm not sure what are you referring to here. All right, I think questions why that is pretty much all right. Any new ideas you think we should work on? Aman, who are you referring to when you say we should work on here? Right. I'm not sure that I understand exactly your question, and I think we're arriving close to the end of the time. Maybe I think we can keep it here. In any case, feel free to reach out to me. I make sure that you get my socials, probably on LinkedIn or something. If you have any questions, I'm always happy to answer them. I hope this presentation was useful, that it shed some light on what are biometric data, how do we use them, why is it not evil in and of itself, and how can it actually improve our privacy in that case. You've really understood the privacy part when we'll talk about zero-knowledge proof and secure multi-party computation. I think the session isn't there yet, but this is really where you'll understand how can we take that sensible information and make sure that it's purely opaque and cryptographically secure. Rebecca, I think I can give it back to you.
Thank you very much for that really interesting session. So many great questions. I can tell everyone found it really interesting. So yeah, we will end it there for today. I've forgotten what our next session is actually. Let me quickly check what that is. Our next session will be on Monday, and I think it's World ID use cases. And then coming up after that, we have 3 sessions by DC Builder, so ZKML, World Chain, and then future work from the Worldcoin communities. So I hope you're all looking forward to that, everyone. We'll end the session there for today. Thank you for joining us again, and we'll see you next week. Yeah, we'll share Tanguy's social media links in the recording. We'll put them under the video so you can connect. Also, any links that you might find useful will be in that description as well. So check that out. The link will be posted in the Discord tomorrow, so you won't miss it. Okay, thank you everyone for joining us. I will drop my email. Otherwise, we'll end the session there. Thanks, everyone. Bye.
Thanks for joining me. Bye.